Hi, I'm Maciej. Some of you may recognize me from Monadic Warsaw. I've been here a few times. I like this meetup very much. So I decided to tell you about a little program I wrote in Haskell. It's interesting, I think, because it's entirely at the type level, and it's a simple HTTP server that serves static files from current directory. And yes, it's implemented using type families and promoted data types in the Haskell type system. So why would I want to do this? Basically to demonstrate what can be done with the powerful type system we have in Haskell. Of course, I'm not the first to notice that it is powerful. There is a few posts on the internet demonstrating how to write simple programs like solving some puzzles, etc. But I wanted to write real programs. So I define real programs as programs that you can actually run and that talk to the outside world. So, yeah. Just let me ask quickly: who here is familiar with the type level programming, like the stuff that Anders showed? Okay, so I'll just show some basic stuff to get you going. As you may know, in GHC we have a lot of extensions. The first useful one we will use today is type families, which you have seen already. That lets us basically define type functions. With some restrictions, which we will lift using this magic keyword, because without this you can't write functions that can potentially put the compiler into an infinite loop. But with come on! Oh. That should. No. Sorry. That's bad. Oh, good. Yes. The second one is data kinds, which you have also seen already. Basically, it lets us define a normal Haskell data type, like this. And with that, you get for free the same data type, but lifted to the type level. So your type becomes a kind, and your data constructors become type constructors. So that's right? Right. So you get a you have just the data constructors, and also they work at the type level. They look the same, but they are interpreted pretty differently by GHC. This means you can use them in type families to compute things. So without this, you would have to do some hacks to use your normal types as data structures, but you don't have to, because you have the promoted data types. So yeah, you can write functions like this. You can evaluate them using kind bank, which is normalizing types. And let me, I didn't explain, this is one way to define natural numbers. So a natural number is 0 or a successor of another natural number. So basically you count the number of s's and you get the number. It's an easy way to define numbers using only algebraic data types, which we have. We actually have built-in natural numbers in GHC, but they aren't useful for demonstration purposes, so I won't use them here. So let me add 2 to 3. Oh, plus, yeah. It just turns off anytime I do anything useful.
I think it just disconnects and then takes like 3 seconds to connect.
Good. Yeah, so we get 1, 2, 3, we get 5 s's, and you can see it works. So that's cool, but how can we write what I call real programs using this? So how can we talk to, read files, write to the standard output, and read input or network? If you ask how is it done in Haskell, you probably can hear some responses like you have a definition main, which is of type IO, and IO is a data structure that defines a imperative computation. It's a type of imperative computations, and your program just computes the description of your computation, like main is put string line hello. You can compose the IO things, but this is just a computation and it's magically executed by the runtime system. That's not how it's implemented in GHC, so it's a lie, but it's a useful lie. And it turns out we can add the IO capabilities to the type level using exactly this way. So let me show you how you can do this. Yeah, let us first let's agree on a representation of strings. We will use the built-in GHC natural numbers, and we will not use the built-in strings because they are useless. You can't. They are basically, you can inspect them using type families. You can concatenate them. So we will use just lists of natural numbers corresponding to character codes, which is totally unreadable. But I've put some comments near each string literal to tell you what is it. Of course, if you are good at reading ASCII, so I can delete them, but you probably aren't. And I do this like map and copy paste this. So I didn't do it manually either. Yeah. So let's write a program that can write to the standard output and read from the standard input. So one good way to define it. So you heard IO is a monad, so you have to put the return. We don't actually have to. Oh yes, we have, because we have to somehow terminate the computation, and it will end with a return unit. We can put a string to the output and do something else. Remember, this is the type of your whole program. So you are just composing some action in front of other actions. You know, it has to contain a sequence of actions, not only a single action. And we can read the line from standard input, and the runtime system will call our continuation with the returned line. Oh, yes, it disappeared. Okay, so what does our program do? It prints a hello world, which is defined here, because it would pollute the code too much. Reads one line from the input, reads, just outputs it with a new line and returns. So, how is it different from normal Haskell? First, if you're writing Haskell, you can, for the continuation to get line, you can just put an inline lambda like this. Main is get line, blah, blah, blah. At the type level, you can do this. Basically, you have to name each of your functions, like in C or other languages that don't have lambdas. Yes, so we are passing the continuation name to the get line, and it's a type family that somehow processes the read line and returns another IO action. So will this compile? This is ugly, right? This is already ugly, and our program isn't even doing anything. And I tell you that it doesn't even compile because you can't do this. So you can't just write simple code like this. And the problem is here. The type level functions is actually quite limited in what you can put here, because if you mention a type family somewhere, like here, it has to be saturated, or so it has to have all its arguments provided. This has to do with the type checking algorithm of GHC, because it would not work if this wasn't the case. So I can write main1 something, but I can just write main1, so it's useless. We have to find some other way to do this, and there is a way to do this. Oh. And it's a thing called defunctionalization. I will just...
Can we invert the colors? Like set BG light?
Actually, is it better? Okay. Okay. So how it works, it's basically you take every lambda in your program and create a data type with that has a each constructor for one, so that has a constructor for each of the lambdas, and its parameters are the variables captured by this lambda. Is that kind of clear?
I think if you show it, it'll be.
Actually, this second program is different from the first, so it will be hard. But I will just write down the program in normal Haskell, just for you to see the correspondence. It's different from the first because it's doing put string line, output string hello world. I'm using my I/O data type, not the Haskell one, so I will just throw in a continuation here, and then I will get a line 1, and get second line, and print the concatenation of them. Sorry?
Could be line 1 twice.
Yeah, right. So how do we do this? First, we lift all the lambdas to the top level, so give them names, because you can just have inline lambdas. So main 1. Get line main 2. Of course, we have to manually thread all the captured variables, because the second lambda was capturing line 1 read from the previous, so we have to pass it here. Yeah, and that's it. And the next step, the functionalization is you gather all the lambdas, and you let me make it clear which variables are captured and which are the actual parameters, and make a data type out of it. And every time you call such a lambda, you replace it with an evaluation function. So you create a type like this, which is exactly here, and you say apply main 1 line 1 is that. Let me just replace it. Yes. So, are you convinced that this is a different representation of the same program? Yeah. So, this is what you have to do with every lambda when you're programming at the type level, which is annoying, and it's even more annoying because my example is deliberately contrived, because there is only one type of functions used. String to IO, actually I lied, yeah. So string to IO action. But if you want to have different types and you want type safety, it doesn't work anymore. It gets even more ugly. I will show you in a moment, but let us just work with this for a while. Oh, I deleted my code. So as you can see, I've done the same thing at the type level, which is apply main1 to line 1, calls another get line, and passes the main2 continuation, which is actually concatenating the lines and returning them. So how do we run this program? We haven't written a runtime system yet, but we can do it probably by hand. It's not that hard. It's not a big program. So I've prepared myself a template for simulating this program. We will provide the two lines AA and BC as input. And let me start. We start with main. So, and we will use GHCI as the evaluation engine. So we will be the outside world, and GHCI will be doing all the computations. So let me evaluate main. Oh yeah, loads. Yeah. Pretend you don't see this hack. Yeah, we can see. We look only at the beginning. That the continuation we will just copy paste over and evaluate again. So it's a put string, and what is the string? Okay, map hello world. Okay, so we just output hello world. Good. And now we have to execute get line main1. It's already evaluated, but so we don't have to. Let me just put it here. Okay, we have get line, so we take one line from the input, and it was AA or 6565, so we have to call main1. Actually apply. Right? We are calling the continuation to the getLine action with the result. Okay, let me evaluate this. Main1. Good. It tells us to get another line from the input. So we give it the line BC or 66, 67. So now we apply the continuation main to 65, 65 with 66, 67. Yes. Main 2. Okay. It tells us to put a string to the output, so let me see. Map. It's ABC, so ABC, and we get to return unit, and we are done. We just run our program. Of course, it's annoying, so I wrote a little program that does this automatically, but I hope it was instructive to see it in person. It's not as slow as me, but it's still slow. We'll see later. Okay, so now we know how to add input and output to our type level programs. So let me show you a demo. of my HTTP server, which I wrote using this style. And then I will show you the code of this, which is kind of more complicated and even more ugly. And we'll see, run. Oh, yeah. It's outputting what expressions it is evaluating. You can see it's doing similar things to what I was doing manually before. So I can see it's listening, it's opening a socket on port 3000, so why don't we go to the web browser and tell it to, for example, download its source. Okay, it worked. Let's see how long it takes. Oh yeah, just 1.71 seconds, not that bad for basically a GHCI evaluating things and also you know, converting arrays of bytes to yeah, it's even better than the B0, B1 that Anders showed. Okay, so yes, I've proved you can do a HTTP server in a Haskell type system. Oh, it even generates dynamic pages. If you put some garbage, it will tell you not found your garbage. So it's pretty advanced. You can still do this, I think. Blah blah blah. I see. Didn't have the time to fix it, but sorry. Okay, let's see the code. Yes, I've changed the set of system calls, as I call them, a bit, because we need some more functionality than just you know, read line and stuff. So exit, actually I don't use it because it's an infinite loop, but it was there. Listen is opening a socket and listening on a given port and giving me a file descriptor, like in POSIX file descriptors. Accept is you give it the socket you get from listen, and it waits for a connection and gives you the file descriptor of the connection. And you can write some bytes to the socket or read some bytes from the socket. You can open a file. This is a file name, and this is the only place where you have error handling. So it returns just a file descriptor of the file if it's there, or nothing if it's an error. This is for the not found message. And you can close the file descriptor, though our program is so inefficient that we could probably safely ignore this. Okay.
Can we change the background again?
Yeah. I've seen a pattern in my type level Haskell code. It kind of looks like a basic or assembly, and I even labeled the columns. So on the left you have the label, you have what you do and where you go afterwards. And if you kind of ignore the garbage that Haskell insists me to write, it's even readable, at least the first part. Yeah, so this is what you already seen in an execution trace. We open a socket, we give it to a accept loop, we accept another socket. Oh, I made a monadic combinator out of it so that I can basically not thread the server file descriptor and all my state through every function. So this is just the loop for accepting clients, and it goes to handle client to handle it. Oh, by the way, this fancy arrow is a notation for my type level functions, but they are after the functionalization magic. It's even more magic than the previous one. So the $$ is our apply, and yes, and this is the type of functions. We get some type safety, and I will show you later how is it done, because it's not obvious to see. Yeah, handle client. So we get a file descriptor from the accept. So we read a request. We assume the request fits in one, just one our buffer size, which is, I don't know. Oh no. Yeah, 4K. It mostly works. And yeah, then we parse the request and give it to that function that. I didn't mention one thing. I said that you have to give all your functions a name, like in C, but actually it's even worse in C in some way, because you also don't have a case expression in the type level. So every time you do case analysis, for example, every time you pattern match, you also have to make it into a type family and give it a name, which is kind of like you would have to lift each of your if statements in C to a named function. So it's bad.
So how do you, where do you have the code that opens a file, for instance?
It's in the runtime system. It's there's a program.
So open the files outside the type level.
Yes, I'm using the approach which is used to, which I said at the beginning. So the program actually computes a description of the imperative action and it's interpreted outside, like I did manually.
So there's a program that goes through that type tree, let's say.
Yes, I didn't show it yet. My phone,
Did you yes, I think your browser set the button on the recording. Well, this is not broken.
Sorry, I'm bad with technology. I will show it later if you want.
You can do it downstairs. Downstairs in the bar.
Yeah. Or if I have time here. So yes, everything here is just abstract nonsense. It's given meaning by the interpreter, which uses GHC as a way to evaluate, to do computations, so to evaluate pure code.
But could you express any pure function as a function in type level?
Yes. As I said, you need this extension because otherwise some restrictions apply to how you can define your type functions. Because if you can express every function, then you can make the compiler not terminate evaluating type check. So yes. And one last thing so the code is straightforward. This is the function that pattern matches on the result of parse request, which is maybe request. And if we see a file name, we take out the slash, we open the file and we go save file, which takes the file descriptor and writes a response. Kinda incomplete without headers, but it's already long, and copies the data from one file descriptor to another. So it's trivial code, but it's unreadable. I don't encourage you to write this stuff. One thing I didn't talk about is parsing, because to make my life easier, I ported parsec to this thing. Here is an example of how you use it. I'll take out the noise. So to parse a request, this is a data constructor. You get a token. It's not exactly following the PHP spec, I tell you. So it's just splitting things on white space. So we get one token which is a request method, another which is the path, and another which is HTTP 1.1. If you know how it looks, it is blah blah. So it's parsing this. This is the first part, this is the second, this is the third, and then it parses the others for no reason because I don't use them. But there's headers. Actually, I don't have to write the examples because I have test for this. And actually, you get one good thing with this compared to normal Haskell, which is you can write your tests and have the compiler evaluate them, and when your code compiles, it will run, because it wouldn't compile if the test wouldn't run. So you basically have to treat GHC into evaluating some equality constraint. So
but this works only because the parse is pure, right? I mean,
sorry? Yeah.
This works only because the parse happens to be pure.
Yes.
Yeah.
Of course, you could write a pure interpreter of the IO data type. And, So, for example, here we are testing the header parser. It should split into two parts. And and if we mess up the tests or code, it gives a type error. So it's kind of neat method of testing. Actually, there's a way to do symbolic evaluation. So if you want to, just put hey here, hey. But I think you need to tweak it somehow to work. Yeah, but there's a way to do this. If you put the type signature outside, I think. Yeah. Okay. I didn't. No. So I had it working, but it's no longer working. So that's it, I think, because I'm out of time. Thanks.